Bridge, tokens, training, and the shape of the problem. Before we can discuss how language models work, we need to understand what they actually work with. The fundamental challenge in building a language model is that computers operate on numbers, while human language is text. We'll establish why tokenization and the training loop matter, and what mental models will help you understand the technical machinery that makes language models possible. Language models don't read text the way humans do. When you see the word understand, you recognize it as a single semantic unit. A computer, however, receives that word as a sequence of bytes representing Unicode characters. The gap between bytes and meaning is enormous. Tokenization is the first transformation that bridges this gap, converting raw text into discrete units called tokens that become the atoms of computation for the model. Think of tokens as the vocabulary of the model's internal language. Just as you learned words in elementary school before constructing sentences, a language model must first establish what its basic units are. This choice has downstream consequences for everything the model does: how much memory it requires, how long sequences become, which languages it can handle efficiently, and even which concepts it can represent clearly. Getting tokenization right is not a preliminary task to be rushed through. It's a foundational decision that shapes the entire architecture. Why does tokenization matter so much? Consider that every decision about how to break text into tokens affects what the model can learn. If we tokenize at the character level, the model sees UNDERSTAND as 10 separate units. This is simple and universal, but it forces the model to learn letter combinations from scratch. The model must discover that TH often appears together, that ING marks participles, that Q is nearly always followed by U. While character-level models can learn these patterns given enough data, they waste capacity relearning linguistic regularities that we already know.
If we tokenize at the word level, understand becomes one unit, which seems more natural. The model treats the whole word as an atom. But what about understanding, or understands, or misunderstand? Are those different tokens? If yes, then we need separate tokens for every inflected form, every derivational variant, every compound. English alone contains hundreds of thousands of distinct word forms, and new words, brand names, technical terms, portmanteaus, appear constantly. A fixed vocabulary becomes obsolete almost immediately. And what happens when the model encounters a word it has never seen during training? Without a mechanism to handle unknown words, the model can only emit a generic unknown word token, losing all semantic information. Modern language models use subword tokenization, a middle ground that breaks words into meaningful chunks. The word understanding might become under plus stand plus ing. This approach captures common patterns while keeping the vocabulary manageable, typically between 30,000 and 100,000 tokens. The algorithm used to discover these subword units is called byte pair encoding, or BPE. BPE starts with individual bytes or characters and iteratively merges the most frequent adjacent pairs until it reaches the desired vocabulary size. The result is a data-driven vocabulary. Common words like the remain as single tokens, while rare words are split into recognizable subunits. Understanding BPE means understanding the trade-off space. Smaller vocabularies mean longer sequences, because more words must be split into subword pieces. Longer sequences mean more computation, since every transformer layer must process every token in the sequence. Larger vocabularies mean fewer splits and shorter sequences, but more parameters dedicated to representing rare tokens. The embedding matrix and output projection layer both scale linearly with vocabulary size. In a small model, the vocabulary parameters can dominate the total parameter count. There is no single right answer, only engineering trade-offs that depend on the expected language distribution, the model size, and the computational budget.
Once text becomes tokens, the next question is, what does training actually mean? When we say we're training a language model, we mean we're adjusting millions or billions of numerical parameters so that the model assigns high probability to real text and low probability to nonsense. This is framed as a prediction task. Given a sequence of tokens, the model predicts what comes next. If the next token in the training data is apple, and the model predicted apple with high confidence, that's good. If it predicted elephant with high confidence, that's bad, and we adjust the parameters to make apple more likely next time. This adjustment process is called gradient descent, and it's worth building a strong intuition for. Imagine you're standing in a foggy valley, and you want to reach the lowest point. You can't see the whole landscape, but you can feel which direction is downward right where you're standing. You take a small step downhill, reassess, and step again. Repeat this thousands of times, and you'll eventually reach a low point. Perhaps not the absolute lowest, but low enough. Gradient descent works the same way. At each step, we calculate which direction in parameter space would most reduce the error, and we take a small step in that direction. The error is measured by a loss function, which quantifies how wrong the model's predictions are. Lower loss means better predictions. The gradient tells us which parameters to increase and which to decrease to improve predictions. The training loop, then, is simple in outline but complex in detail. We feed the model a batch of token sequences, compute predictions for each position, compare those predictions to the actual next tokens, calculate the loss, compute gradients that tell us how to adjust parameters, and update the parameters. Then we repeat this thousands or millions of times, slowly improving the model's ability to predict text. Each iteration is called a training step. A full pass through the entire training dataset is called an epoch. Large models are typically trained for just one or a few epochs on massive datasets, because collecting diverse text is easier than repeating the same examples.
But why do we train in batches rather than one sequence at a time? Batching is fundamentally a hardware optimization. Modern GPUs and TPUs are designed to perform the same operation on many pieces of data simultaneously, a property called data parallelism. Processing 100 sequences at once is not much slower than processing one sequence because the hardware can parallelize the work across many computational units. Matrix multiplication, the dominant operation in neural networks, achieves vastly higher throughput when operating on large batches because the hardware can amortize the overhead of memory access across many examples. This means batching dramatically increases throughput. You process more tokens per second, making better use of expensive hardware. However, batches also consume more memory, and memory is limited. Every sequence in the batch requires storage for its activations, the intermediate values computed during the forward pass that must be kept for the backward pass. If your batch size is too large, you exceed the GPU's memory capacity, and the training crashes. Choosing a batch size is another engineering trade-off. Larger batches improve hardware utilization and can lead to more stable gradient estimates, but they require more memory and may affect how well the model generalizes to new data. Some research suggests that very large batches can harm generalization unless the learning rate is carefully adjusted, adding another dimension to the tuning process. Another foundational concept is the shape of the computation. When we multiply a batch of token sequences by a model's weight matrices, we're performing matrix multiplication at scale. Matrix multiplication is the core operation in neural networks, and its computational cost is determined by the dimensions of the matrices involved. If you have a batch of size 64, a sequence length of 2,000 tokens, and a model with hidden dimension 4,000, the number of operations scales as 64 times 2,000 times 4,000 times 4,000. The hidden dimension appears twice because matrix multiplication combines one dimension from each matrix and produces a result whose size depends on both the input and output dimensions. This quickly becomes trillions of operations per training step. Understanding these shapes is essential because they determine whether training is feasible. If a single forward pass through the model requires more memory than your GPU has, the training won't run at all. If the computation is too slow, training will take months or years, longer than the research cycle permits. Engineers spend significant effort optimizing these shapes, choosing model dimensions and batch sizes that balance accuracy, speed, and hardware constraints. Sometimes a seemingly small change, like reducing the batch size from 128 to 64, makes the difference between a training run that completes and one that crashes.
There's also a subtlety in how shapes interact. You might assume that doubling the model size doubles the training time, but it's not that simple. Memory access patterns, cache efficiency, and the parallelism within matrix operations all affect real-world performance. Some shapes are friendly to hardware, hitting sweet spots where the GPU can operate at peak efficiency. Other shapes cause underutilization, where the hardware sits partially idle. Learning to recognize these patterns requires experience, but it begins with understanding the basic relationship between dimensions and cost. One more concept is crucial: the difference between training and inference. During training, we process entire sequences at once because we know all the tokens already. They're in the training data. We can compute predictions for every position in parallel using a technique called teacher forcing. The model predicts the second token given the first, the third token given the first two, and so on, all in a single forward pass. This parallelism is what makes transformer training feasible at scale.
During inference, when the model generates new text, the situation changes. We don't know future tokens yet. We generate one token at a time, conditioning each new token on all previous tokens. This sequential generation is inherently slower than training because we can't parallelize across the sequence length. Each new token requires a full forward pass through the model. For a sequence of 200 tokens, that's 200 separate forward passes, each depending on the previous one. This sequential dependency is why inference has different computational characteristics than training, and why techniques like caching intermediate results become important. Understanding this distinction explains many design choices in model architecture and deployment infrastructure. In the next lecture, you'll walk through the mechanics of tokenization algorithms, the implementation details of the training loop, and the matrix operations that underlie everything. You'll see code for BPE, learn how vocabularies are constructed, and trace through exactly how gradients flow backward through the model. To follow that lecture effectively, keep these mental models in mind. Tokenization is about choosing the right granularity of linguistic units. Training is iterative parameter adjustment guided by prediction error. Batching is a hardware optimization that trades memory for speed, and the shape of matrix operations determines computational cost. Why does this all matter beyond the mechanics? Because every choice here ripples through the entire system. The tokenization scheme affects how well the model handles morphologically rich languages, code, or mathematical notation. If the BPE vocabulary was trained primarily on English text, it might split Arabic words into awkwardly short fragments, or represent Chinese characters inefficiently. Programming languages have their own tokenization challenges. Should variable underscore name be 1 token or 3? Should indentation be tokenized explicitly? These choices affect how well models understand and generate code.
The training loop design affects how quickly experiments iterate and how much compute is required. Small decisions about batch size, learning rate scheduling, and gradient clipping compound over millions of training steps. A poorly chosen learning rate might mean the difference between a model that converges in 2 weeks and one that never converges at all. The batch size affects both training stability and final model quality. Too small, and gradient estimates are noisy. Too large, and the model may fail to generalize. Understanding these foundations means understanding why language models are built the way they are, and what constraints shape their design. As you listen to the next lecture, notice how each technical detail connects to these broader themes. When BPE merges the most frequent byte pairs, think about why frequency matters and what happens to rare words. A word that appears once in the training corpus will never get its own token. It will be split into subwords based on patterns from more common words. This can lead to surprisingly long tokenizations for technical terms or proper nouns. When the loss function is computed, think about what it means for a model to be uncertain and how that uncertainty is quantified. Cross-entropy loss, the standard choice, heavily penalizes confident wrong predictions. If the model assigns probability 0.9 to the wrong token, the loss is much higher than if it assigns probability 0.6 to several plausible tokens. When matrix dimensions are discussed, think about how those dimensions translate to memory requirements and floating point operations. A weight matrix of size 4096 by 4096 contains nearly 17 million parameters. If stored as 32-bit floats, that's 64 megabytes for a single matrix. A transformer with 48 layers has dozens of such matrices, and the memory adds up quickly. The next lecture provides the how. This bridge provides the why and the conceptual framework.
Tokenization and training loops might seem like dry preliminaries, but they are the foundation on which everything else is built. Without a principled approach to converting text to tokens, models can't learn language structure. A model that tokenizes running as run plus ning can potentially learn that these two tokens together indicate present progressive aspect. A model that treats running as an atomic token must learn this word's meaning independently from run, runs, ran, wasting capacity on redundancy. Without an effective training loop, models can't adjust their parameters to fit data. The choice of optimizer, learning rate, and gradient clipping determines whether the loss decreases smoothly or oscillates wildly. These are not incidental details. They are the core machinery that makes language models possible. In summary, we've established why tokenization matters, what training fundamentally is, how batching and matrix shapes constrain design, and why these foundations are essential. The next lecture will give you the implementation details and mathematical rigor to see these concepts in practice. Listen for the connections between abstract principles and concrete code, and you'll come away not just with knowledge of how language models are built, but with intuition for why they work the way they do.